Leia here from leiaforsci.com, and in this MCAT General Chemistry video, we're going to look at molarity, molality, and molar mass. Let's start with a quick overview. Mass gives us the amount of matter of a substance. Mass is not equal to the weight of a substance, because if you think back to physics, weight is a force, and force is equal to mass times acceleration, in this case mass times gravity, which means if the gravitational force changes, so does the weight. The weight of an object will be different on the surface of the Earth, orbiting the Earth, on a different planet, on the Moon, but the mass will always stay the same. That being said, if you assume that the average MCAT experiment is taking place on Earth, you can think of mass as weight, so long as you understand the technical difference. Molarity and molality are different ways to represent concentration, where molarity big M is equal to moles per liter, and molality little m is equal to moles of solute per kilogram of solvent. If you have trouble differentiating between solute and solvent, think of a martini glass with an olive in it. The solvent is the thing that holds everything, that's the martini glass, and the olive is the upside down U, it's the solute, it's the thing that goes into the martini glass, into the solvent. Molar mass, as the name implies, is the mass or the amount of matter that a mole of something takes up, where a mole is a very large number, 6.02 times 10 to the 23rd. Molar mass is represented in units of grams per mole. Let's go ahead and break it down so we can see everything in more detail. We said that mass is the amount of matter of a substance, and this is measured in SI units of kilograms, where the prefix K for kilo is equal to 10 to the third or 1,000 of. A kilogram is 1,000 grams. US students, if you're used to measuring things in pounds, let's put this into context. A kilogram is heavier than a pound, where 1 kilogram is equal to 2.2 pounds. That means a kilogram is more than twice the size of a pound, or look at it the other way, 1 pound is equal to just 0.45 kilograms. The good news is, the MCAT will only test you in SI units. That means you don't need to memorize these conversions. It's simply for you to wrap your mind around the difference in weight between a pound and a kilogram. If mass tells us the amount of matter of a substance, molar mass tells us the amount of matter of 1 mole of that substance. In the last video, we saw that the mole is a very specific large number for calculating atoms and molecules. We know a pair equals 2, a dozen equals 12, and a mole is equal to 6 times 10 to the 23rd. But that's just the number, the amount of pieces in a mole. A dozen papers, very light. A dozen eggs, a little heavier. A dozen books, now it's getting really heavy. It's the thing that you're counting that will determine the mass. And when it comes to counting a moles have a specific mass depending on the type and number of atoms, and you find that mass on the periodic table. This table gives you at least 2 decimal spaces for many of the atoms. On the MCAT, just round it to the nearest whole number. If we're looking for the mass of a mole of hydrogen, it would be 1. For the molar mass of hydrogen gas, which is H2, we simply take 2 times the mass of hydrogen, which is 2 times 1, giving me 2 grams per mole for hydrogen gas. The mass of a mole of hydrogen gas will be 2 grams. If I want the molar mass of H2O, this is something to memorize. I need to find the mass of the sum of the individual moles of atoms. That means I have 2 times hydrogen and 1 times oxygen. 2 hydrogens weigh 2 grams, 1 oxygen weighs 16 grams, 2 and 16 is 18 grams per mole. Another one to memorize is glucose. What if I asked you to find the mass of half a mole of glucose? To find the mass of half a mole of glucose, we first have to find the molar mass of 1 mole of glucose, and then take half of that. Glucose is something you should know as C6H12O6. In fact, you should also have the molar mass memorized, but let's calculate. To find the mass of glucose, we have to find the mass of carbon times 6, hydrogen times 12, and oxygen times 6. Add up the masses, and that'll give you the total molar mass. Looking at the periodic table, hydrogen is 1, carbon is 12, oxygen is 16. Remember, we round to the whole number. So we set it up as 12 times 6 plus 1 times 12 plus 16 times 6. 12 times 6 and 1 times 12 is really just 12 times 7. 12 times 7 is a number you should know as 84. 16 times 6 is tricky. Think of 15 times 6, which is 90. Add another 6, giving you 96. And then we add it up. 80 and 90 is 170. 4 and 6 is 10, giving you 180. For a molar mass of 180 grams per mole. But we're not done. We're looking for half a mole of glucose, so we set it up given times ratio. Half a mole of glucose is my given, times the ratio of moles at the bottom so we can cancel, and grams at the top. The molar mass of glucose is 180 grams per mole. This allows us to cancel moles with a final unit in grams, leaving us with a calculation of 0.5 times 180 over 1, or 0.5 times 180. Decimals multiplication too complicated. Just think of it as 0.5 is equal to a half. What is half of 18? 9. And then add that 0 back, which is 90. The other option is the decimal trick, 5 times 18, way too complicated. But half of 180 is 90, giving us 90 grams as the mass of half a mole of glucose. Molarity, written as big M, is measured in units of moles per liter, where mole refers to the solute or the thing that you're dissolving, and liters refers to the total volume of solution, meaning the total volume of the solute and solvent together. The molarity number is typically written in brackets. For example, if you're told that an NaCl solution is equal to 0.5 molal, where molal tells us the molarity of this NaCl solution, we have 0.5 in brackets, which is equal to moles per liter. That's 0.5 moles of NaCl per 1 liter of solution, where the 0.5 represents the moles and the 1 liter is self-understood as the ratio between the moles and the volume. Does this mean the solution has to be exactly 1 liter? No. This is simply a ratio telling us that for every 0.5 moles of NaCl, we have a total of 1 liter solution. If we cut it in half so that we have 0.25 moles of NaCl, the entire ratio has to be halved, giving us 0.5 liters of solution. If we cut this in half for 0.125 moles of NaCl, the volume also drops to 0.25 liters, and so on. Let's prove this mathematically to find the molarity of a solution that's created by dissolving 0.125 moles of NaCl in 0.25 liters of solution. We set this up so that molarity is equal to moles per liter and fill in what we're given. We have 0.125 moles divided by 0.25 liters. We can't cancel any of the units, but we recognize that moles per liter is the unit for molarity, then we just need the number. 0.125 over 0.25 looks really scary without a calculator. So the first thing you might want to do is move the decimal so that you have a whole number in the denominator. We'll use the decimal trick taught in the MCAT Math series linked below and move both of them over 2 spaces. This gives me 12.5 divided by 25. You should recognize that 12.5 is half of 25, so you can divide both top and bottom in your head by 12.5, giving you 12.5 divided by itself is 1, 25 divided by 12.5 is 2, or just recognize that when one is half of the other, your fraction is a half, which is equal to 0.5 molar, which is what we predicted from the very beginning. On the MCAT, many of the experiments are going to deal with tiny amounts, where you'll be given milliliters, micromolar, and smaller numbers that you have to convert. Say you're told you have 30 milliliters of this 0.5 molar NaCl solution, and you're asked to find the number of moles. We'll use given times ratio the way I teach in the conversion series linked below, and start with our given of 30 milliliters. We know that we want to find moles, and the relationship between milliliters to moles is not clear. What we do know is that the molarity equation is moles per liter, which gives us a direct path to moles if only we can find the path to liter. So that will be our first ratio, converting from milliliters to liters. We set this up so that milliliters is on the bottom and liters is on top, and add the conversion where 1 liter is equal to 1,000 milliliters. This allows us to cancel milliliters and gives us liters as the answer. The next conversion we want to use is going to moles from liters, which is the molarity in units of moles per liter. For this specific molarity, we have a ratio of 0.5 moles per 1 liter, which allows us to cancel liter, giving us our final answer in moles as desired. Then we just carry through the math. We have 30 times 0.5 divided by 1,000. I don't like dealing with decimals and fractions at the same time, so let's use the decimal trick also taught in the math series, moving 1 to the right, 1 to the left. This gives me 3 times 5, which is 15 divided by 1,000. And let's use the decimal trick one more time, where 1,000 gives us 1, 2, 3 zeros to the left, 1, 2, 3 zeros to the left, for a final answer of 0.015 moles. If you recognized that your MCAT units were given in millimoles instead of moles, you could have stopped when you had 15 over 1,000 moles and recognized that 15 divided by 1,000 is 15 times 10 to the minus 3. Millimoles would be moles times 10 to the minus 3. So this cancels to give us the milli, and our answer is 15 millimoles. Say you didn't know this trick and you wanted to convert your moles to millimoles mathematically. We can set this up as a new given times ratio equation. We have 0.015 moles as our given, and we need a ratio of moles to millimoles. Mole goes on bottom to cancel, putting millimole at the top, and we know that 1,000 millimoles is equal to 1 mole. From here we multiply 0.015 times 1,000, or use the decimal trick. For 1,000 millimoles, we move the decimal 3 times to the left, so we move this one 3 times to the right, giving me 15 times 1, which is 15. Moles cancel, giving me an answer of 15 millimoles. Molality is another form for concentration, which I personally find slightly more annoying, but it's very useful in density problems. Molality is written as a little m because a big one was already taken for molarity. This is measured in moles of solute divided by kilogram of solvent, not solution, just solvent. Say you're asked to find the molality of solution formed when you mix 105 grams of NaCl with half a liter of water. To find the molality, we need to set up the equation. We have molality is equal to moles per kilogram. Moles would be NaCl, but all we're given is grams, so let's convert. Let's set up a given times ratio where our given is 105 grams of NaCl, and the ratio will be the molar mass of NaCl as we just learned how to calculate. Instead of setting it up as grams per mole, we need grams on the bottom to cancel and mole on the top. What is the molar mass of NaCl? The molar mass of NaCl was 23 for sodium and 35 for chlorine, which gives us 58 grams per mole. We fill this in as 1 over 58 and solve. I don't know about you, but I don't know how to do 105 over 58 in my head. But on the MCAT, close enough is good enough. We can round 105 down to 100. We can round 58 down to 50, giving us 100 over 50, which is 2 over 1 or 2. On the calculator, we get 2.1, which is close enough. Which means for molality, we have 2 moles of NaCl divided by half a liter of solution. But we need kilograms, not liters. You should memorize the density of water as equal to 1 gram per milliliter. In this case, we're looking for liters, so let's apply the conversion once mathematically, then memorize the answer, so you never have to do this again. 1 gram per milliliter is our given. The ratio would be the conversion from milliliters to liters, which is 1,000 milliliters over 1 liter. This allows us to cancel milliliters, but our answer is going to be very big, and since the SI unit for mass is kilograms, why don't we run a second conversion by adding the ratio of grams at the bottom to cancel kilograms at the top. We know that 1 kilogram is equal to 1,000 grams, allowing us to cancel grams, giving us a final unit of kilograms per liter. And guess what? 1,000 cancels out, which means we have 1 times 1 times 1 divided by 1 times 1 times 1. In other words, 1. The density of water is equal to 1 gram per milliliter, or 1 kilogram per liter. This helps because if you're given any volume of water in liters, you can just use that same number for kilograms. So half a liter of water under standard conditions will be half a kilogram. And finally, we solved 2 divided by 0.5. I despise calculating fractions and decimals, so let's see how we can simplify. We have 2 divided by 0.5, so we can do this the long way. Get rid of that decimal by using the decimal trick. Move both to the right, giving me 20 over 5, which is a fraction you should know. 20 divided by 5 equals 4. Another way to think of this, back from your middle school math, is whenever you divide by a fraction, you multiply by the reciprocal, which means 2 divided by 1/2 is equal to 2 times the flip of 1/2, or 2 times 2 over 1, which is equal to 4. A final way you can think of it is any number divided by a half is always going to be times 2, as we just showed. And that's another way to get our answer as 4 molal. Molar mass has to do with just the one thing in question. If you're asked for the number of moles of 25 grams of NaCl, all we care about is NaCl. We set it up as given times ratio, 58 grams for 1 mole. Grams cancel, leaving us with 25 over 58. This is going to be about 25 over 50, which is a half. Because we're rounding the denominator down, our answer will be too high, so we'll say that it's something less than 0.5. Calculator gives us 0.43. But it's straightforward. Molar mass is just that one thing. When it comes to concentration, it gets confusing, especially looking at the difference between molarity and molality. Both of us let us calculate concentration, it's just a question of what we take into account. Molarity uses solution, molality uses solvent. If you're given a question on the MCAT, how do you know which one to use in each situation? The major difference is that molarity takes the entire solution into account. In our example of 0.5 molar NaCl, we said we had 0.5 moles NaCl for every 1 liter of solution. What is a solution? Everything mixed together. That means the total volume of 1 liter is equal to the volume of the water mixed with the volume of the NaCl. Even though we put just a little bit of salt into solution, that salt does have volume and it will contribute to the total volume of solution. Molality, on the other hand, only takes into account the volume of the solvent, and that means whatever you're dissolving to get your molality is not contributing to your math whatsoever. You will always have a specific mole to the specific solvent. No matter how much volume is contributed by the solute, it will not change the molality calculation. How do we make that 0.5 molar NaCl solution? Here's how I want you to think about it. If we want to make a 0.5 molar NaCl solution, we take 0.5 moles of NaCl, just scoop some salt, weigh it out, drop it into your beaker, and then you pour the water in until the volume reaches 1 liter. We assume that the volume of the NaCl is negligible, but let's say it's not. This is not coming off a table. I want you to pretend that these numbers are correct. Let's say that the volume of the NaCl is equal to 0.01 liters. When we have 0.01 liters to start, and then you add water and you add water till you get to that 1 liter mark, if 1 liter is equal to the total, that means we subtract 0.01 liter to give us only 0.99 liters of water added. It's not an entire liter of water, it's 99% of a liter. If we want to find the molality of this solution, it would not be the same number. Molality would be 0.5 moles of NaCl divided by 0.99 kilograms of H2O. Now, for the sake of the MCAT, close enough is good enough, and we would round 0.99 up to 1, which would still give us a 0.5 molal solution. But this is only the case when your solution is so dilute that the volume coming from the solute is negligible compared to the volume of the solvent. In fact, that's a good trick for the MCAT. If you're dealing with a dilute solution, just assume molarity and molality are the same and simplify accordingly. However, if the solution is not dilute, you can no longer make that assumption. I want you to imagine that you're making a flavored drink. In the first situation, imagine that you're adding flavored powder to a beaker. Then you add enough water to hit the 1 liter mark. In this situation, volume of the powder is going to be about 0. Think of the tiny amount of powder or Kool-Aid in an entire liter of water. For the second flavored drink, I want you to imagine you drop 2 strawberries into the beaker, a couple of mint leaves, and maybe even some lemon juice. Now, when you add water to get that beaker to the 1 liter mark, are you adding about 1 liter of water? Or maybe the volume of the strawberries and the mint leaves and the lemon juice are taking up so much space that you wind up putting in something like 0.8 liters or 0.7 liters. In this situation, the volume of the solute, the strawberries, the mint leaves, the lemon juice, are very significant to the calculation. And if you had to calculate molarity versus molality, molarity would use 1 liter as the total solution, but your molality calculation would use just the water, 0.8 kilograms for the 0.8 liters, 0.7 kilograms for the 0.7 liters, giving you a completely different answer. I know it sounds super technical, and it is, so go back to the trick. If your solution is dilute enough, where the solute volume is negligible, just think of molarity and molality as approximately the same thing. For more molarity and molality questions, be sure to try the MCAT Reactions in Stoichiometry practice quiz. First, give this video a thumbs up, then find the quiz on my website along with this entire video series, layerforsci.com/reactions.